All right, here we go for lesson 3 of chapter 15 through probability. Today we are looking at the idea of conditional probability. So doing a probability with some kind of given condition that sort of changes what you have to look at. And so here's kind of the main idea for today, just finding a probability of an outcome based on a certain condition. So here's a really simple example for that. If we said, what's the probability of rolling a 6-sided die and getting a 2? So let me just stop right there for a minute. Normally, if that's what we had, if we just said, what's the probability of rolling a 6-sided die and getting a 2, right, we would say, well, let's look at the sample space. So here is a 6-sided die, that's the sample space. And we would say, what's the probability of getting a 2? We'd say, well, there's one of those out of the 6, and that would be our probability. But you're going to see today, we're going to be given some additional information that's going to change the probability, because if I give you more information, you may not have to look at all 6 cases. It might change what you get to look at and actually make the probability greater for something happening. So in this case, it says, given that the outcome is even. Well, if the outcome is even, if I know that, if that's a given, I certainly wouldn't consider all 6 possibilities. We would change our sample space, and if I said, well, given that it's even, that means I'm only going to consider the even values on that 6-sided die. And so now I would look at that and say, well, if I know it's going to be even, then there's only one out of the 3 that I would look at. And so the given scenario, or the condition that we're given, changes your sample space. There's less to look at because we have more information. And so we can eliminate what we know is no longer an option and just consider the given information. So one thing that you got to see as kind of a main part of today's formula is the given becomes your denominator, right? When we said given that it's even, well, there are 3 even scenarios here, and so that's what made up the 3 that we have in our denominator. So again, you got to recognize that the given is your denominator as we go to do this. And so there is a formula for conditional probability. It looks like this. This is in your formula packet, so that will be there for you. But if we said, what's the probability of something happening given that we know this information, this is how we're going to set that up. So again, this line represents the word given right here. So again, if this is my given information, that makes up the denominator within our setup here. And so that's a key part of this. So what's the probability of this and this happening out of this? So again, if I were to sort of apply the formula to what we said up here, if I said, what's the probability of rolling a 6-sided die and getting a 2 given that the outcome is even? So what's the probability of getting a 2 given that the outcome is even? We would say, well, what are the cases where I could get a 2 and an even number within this scenario? Well, how many ways? So ignore the bottom for just a minute. What's the probability of getting a 2 and an even number? Well, look at our sample space here. 1 out of the 6, there's 1 out of 6 ways of doing that. And so if we said, okay, well, this is the probability of getting a 2 and an even number, and if we look at the denominator as this probability, so the probability that it's even, we'd say, well, there are 3 out of the 6 cases that are even, and so if I did this divided by this, right, I can eliminate the commonality there, and I'm just left with 1 over 3. So the one thing I wanted you to see out of this is there's more than one approach. I can use a formula if the formula makes sense to use, or I can use the idea of a sample space and get my answer this way. So I did it this way without the use of any formula. This was pure formula. So I could do it either way and still get that same result. All right, so moving on down here in the next part of this, kind of like what we did in the last lesson, I want to show you some cases where it's just pure formula. There's no word problem to this. It's just a matter of purely working with numbers and formulas to get some answers here. So starting off with our given information, we know the probability of event A is 50%, probability of B is 30%, A or B is 60%. And so let's start by just figuring out how do we get the probability of A and B. Oftentimes the way the students want to do this is they want to just multiply. They want to say, oh, well, A and B, I simply can multiply A times B and get that answer. You can't always do that. I want to show you really quick the difference on when you can and can't do that. If you look at your formula packet for a minute, here's when you can multiply A times B in order to get A and B. Only and only if they tell you that the events are independent events. If we don't know that the events are independent, you can't do this. And the problem that we're doing right now, they say nothing about the events being independent, so I can't just do this times this in order to get A and B. So you have to be really careful. They have to tell you that the events are independent for you to do that. So what we can do instead is make use of our other formula that we looked at in our last lesson, which says that the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. And I can make use of that formula because they said nothing about having independent events. So if I plug in the numbers that I have for this, 0.6 represents A or B. They told me that 0.5 is A, 0.3 is B, and that's what I am solving for. And so if I do the math on that, I can figure out that A and B is 0.2 if I solve for x. So in this case, A and B is 0.2. Keep in mind, right, if I were to have just done 0.5 times 0.3, I would not get 0.2. So really important that I don't do that unless they tell me something about the events being independent of each other. All right, here's a new formula for today. Again, this is in your formula packet as well, but it's simply the probability of A and B out of the probability of B. So again, your given always goes on bottom. That's always going to be the case. So if I just plug in the numbers, I now figured out that A and B is 0.2. And so right up here, I can put my 0.2 in there because that's what we just figured out within the last problem. I know that B is 0.3. And so I can just multiply the top and the bottom by 10 to figure out that my probability is 2/3. Do keep in mind, if they would have given me this to start with, I still would have had to have done this in order to figure out A and B so that I could use it right here. And so that still became kind of a necessary step within doing this formula that you see right here. What about this one right here, the probability of not A given B? So for this, if I still kind of make use of our formula, remember the formula for the conditional probability says on top we do this and this on top and then this on bottom. So again, I'm going to do the same idea here. I'm going to say this and this on top. So on top we're going to do not A and B, and on bottom we just put the given, which is B. So how do we find the probability of not A and B? So if you kind of consider what we did before with this, when we looked at Venn diagrams in the last lesson, we said, well, how do we figure out the stuff that's not in A and is in B? Well, really quick look at the Venn diagram for that. Remember, this is what we did in our last chapter, so we got to make use out of these things. So if we're going to identify this as A and this as B, what are the things that are not in A and are in B? Well, that would be this area right here. All right, those are the things that are not in A and are in B. We refer to that as B only values. So how do we get that? Well, we take all of B, all of set B, which is 0.3, and we subtract that middle portion of A and B, which we already know now is 0.2, and we put it out of B, which again is 0.3. And so that's what our setup would look like in order to figure that out. So again, if we have a scenario like this that does not directly fit a formula that we have, a Venn diagram is a great way of identifying what that number should be. And so there's a good way to do that. So in this case, if I do a little cleanup, I'd have 0.1 over 0.3, which is 1 over 3. Would become our answer for that one. All right, moving on. So for the rest of this chapter, the use of tree diagrams becomes a really helpful tool. And so tree diagrams are best used anytime you're dealing with more than one event. So if I am tossing a coin 3 times, or if I am pulling 2 cards from a deck, that's 2 events. But anything that has more than one event is a great candidate for a tree diagram. So I'd consider the use of these for any time you're doing something than more than one event. If we just said I'm pulling a card from a deck, or I'm rolling a pair of dice once, those are not things I would use a tree diagram for, because it's only one event. But tree diagrams are great when you're dealing with more than one event. So in this case here, we have a box that contains all these cubes in it. It says a cube is drawn. We put it back, and then a second cube is drawn. So notice there are 2 events here taking place. So we're going to make use of a tree diagram for this one. And the first branches of my tree are for the first event. So if I'm going to draw a cube, right, this is my first event. So we're going to draw a cube. Well, what are the possible scenarios I could get? Right, it could either be black or red. So let's consider both cases. This will be the probability that it's the black cube, and this will be the probability that it's a red cube. So let's identify those. So we know what our tree represents. So could either be black or red. Well, what's the probability that I get a black cube? Well, there are 3 of those out of 7 cubes. So 3 out of the 7 are black. The other 4 out of the 7 are red. And that's our first event. Then we have a second event. Notice that after I draw the cube out, I am putting it back, and that makes a big difference. If I were not putting it back, that would change what happens after this, and I'll show you in a minute. So we're going to draw a second cube. This is going to be our second event, right? It's still out of 7. These are still in the box because I replaced the first one that I took out of there. So we're going to look at our second event right here. So this is our first event, and this is now going to be our second event right here. Well, let's branch off of this. Let's just say, well, what if I did pull a black one out of the box? What could happen on my second draw? Well, if I took a black one out first, what could happen on my second event? Well, I could again either get a black one or a red one. And because I replaced my first cube, those probabilities don't change. There's still 3 out of the 7 that are black. There's still 4 out of the 7 that are red. Right? And those probabilities didn't change. Had I not replaced the first one, so let's just say for a minute that they said you do not replace the first cube. Well, if I would have pulled a black one, then now there would only be 2 black ones left in the box, and there would only be 6 cubes left in the box. So this would have become 2 out of 6. Again, if I would have taken a black one, there would still be 4 red cubes, but there would only be 6 cubes left in the box. So this would have become 4 out of 6 and 2 out of 6 if this were not replaced. But let's go on. So down here again, let's consider now the other scenario. What if I would have taken a red one out on my first event? What could happen next? Well, I could again either get a black one or a red one on my second pick. And again, the probabilities didn't change simply because I replaced the first cube. So this is still 3 out of 7, and this is still 4 out of 7. So just for a minute so that we can see the possible cases. This represents the case where I got a black one on the first one and a black one on the second one. So let's say black, black. And how do we figure that out? We simply multiply the two events together, and it would be 9 out of 49. So 9 out of the 49 cases could be black then black. What about the case where I got a black one and then a red one? So if I multiply those together, I get 12 out of 49. So that's black then red, and it's 12 out of 49. Well, what about the case where I got a red one on my first pick, but a black one on my second pick? If I multiply those together, red then black, again, it's 12 out of 49. And then last case, what about the scenario where I got a red on the first one and a red on the second one? Multiply those together, and our red case is 16 out of 49. Something you got to notice about this, if I were to add those four cases together, they would add up to 49 out of 49, which is 1. So these are the only four possible scenarios that could exist within this event. So that's really important. But now that you have a great tree diagram to look at, it's going to make answering these questions extremely simple. There's going to be cases on a test where you are asked to show a tree diagram, and it's important that you do all the work, even this right here where you lay out the ending scenario. So don't forget this part of your tree diagram. It's important. So what about now the case where I had both black cubes come out of there? Really simple, because we've already identified what that is. It's 9 out of 49. So again, that tree diagram makes answering that question really easy. What about the case where I only get exactly one black cube? Well, let's take a look at those. Right here and right here are the two cases where I got exactly one black cube. When you're answering these questions, you always add the cases to figure out your final answer. So when you're doing the tree diagram, from left to right, you multiply, but from top to bottom, you add. And so I am now doing this plus this to get this answer. So add those together, and you get 24 out of the 49 cases have it only one black cube. So quick side note on this. Remember, this is like our OR scenario. So that means I could get this or this, which is why I'm adding those together to get that idea. What if it said at least one black cube? If it said at least one black cube, then I would have done this plus this plus this, because all three of those have at least one black cube. Anyway, let's go on to the new one. This is our conditional probability case. So the probability that they are both red, given that the first one is red. So let's make use of our new formula today. So in the given scenarios, so A given B, remember the formula is the probability of A and B over the probability of B. So whenever you're figuring out the top, again, it's the probability of this and this happening. So I need the probability where I get a red, and the first one is red. Let me just write that one out. So that's kind of the idea for the top over the given. So the probability where the first one is red. So again, the best way to look at this part of the formula, because this is usually the part that people get wrong, is the top. You are looking for cases where both statements are true. This happened and this happened. So of those four cases, where do you see a case where they were both red and the first one was red? Well, this is the only case that fits that scenario. In this case, they are both red and the first one was red. So 16 out of 49 is the only one that fits that scenario, right? Where they were both red and the first one was red. On bottom, you only put the given, where, so for the bottom part, I'm looking for cases where the first one was red. So where do you find cases where the first one was red? Right here and here. So these are the two cases where the first one was red. Remember, I always add downward to get these, so it could have been this or this. So if I add those together, I get 28 out of 49. So that's my given. And now if I cut the 49s out, I am left with 16 over 28, which of course you could reduce. And we could leave it as 4 out of 7. So again, that's my key to you, because these are going to be the hardest problems within the chapter. My advice to you in viewing this formula is, again, whenever you're doing conditional probability, the numerator represents all the cases where both of these statements are true at the same time. They're both red and the first one is red. So I started out by just looking for all the cases where both of these statements were true at the same time. The denominator is always your given. So in this case, I looked for all the cases where the first one was red, and those cases went on bottom. And so that's just sort of the best way of viewing that formula. But make sure you make use of these tree diagrams anytime you have more than one event. They're really helpful.